In this video, we will be discussing the next area of study in VCE chemistry, which is the rate of reaction. We will be covering collision theory, factors that can influence the rate of reaction, and also talk about ways we can measure reaction rate. So first, let's look at collision theory. So what is collision theory? Well, for a chemical reaction to occur, reactants must collide in the correct orientation. So let's have a look of one example. The reaction between hydrogen gas and chlorine gas to produce hydrogen chloride. So let's look at two different arrangements. So this is one potential arrangement, and this is another potential arrangement. Which arrangement is easier to form HCl? Well, this reaction is much easier. See, if they collide, the bond can form very easily. Whereas for this one, if you collide, then it's difficult for the chlorine atom and hydrogen atom on the side to react. So only this orientation would result in chemical reaction, and this one would not result in chemical reaction. Also, aside from having a correct orientation, we also need to overcome activation energy. Which is commonly depicted as EA, activation energy. So what is activation energy? So it is the minimum amount of energy required to break the existing covalent bond of the reactants. Since we are usually talking about reaction of gases, that's why we have covalent bond. Okay, so now let's move on to summarize this a little bit. So the rate of reaction is dependent on two things. So the first thing is the frequency, and the second thing is the success rate. If we can increase the frequency of collision, then there are more collisions with the correct orientation. And this is very good because we need correct orientation in order to have a chemical reaction to occur. But this is not enough. We also need to know the success rate. So this depends on how much or how many collisions with energy bigger than the activation energy, bigger or equal to the activation energy. Only if those two conditions are satisfied, we would actually get a chemical reaction. And if we can somehow increase the frequency or to increase the successful rate of collision, we can increase the rate of reaction. So this is the idea of reaction rate. And now let's look at the factors that can actually change the reaction rate of a chemical reaction. The first one is surface area. So this is for solids only, because there's no point talking about the surface area of water or aqueous solution or surface area of a gas. So by grind solid into fine particles, we can create more space for collision to occur. And this can increase the frequency of collision, thus increase the rate. Always remember to go back to this key theory. You can either increase the frequency or you can increase the success rate. So that's the only two factors that can change the rate of reaction. The second factor is concentration. So this is for gas and solutions. Of course, no point talking about concentration of a solid. Doesn't make any sense. And the idea is the same. If the concentration is higher, you have more reactant particles for a given volume. This in turn would increase number of collisions, which then means you have more successful collision. So why is this the case? Given a particular success rate, if you have more collisions, then you would have more successful collision. So this is the logic behind my argument. The third factor is increase in temperature. And this is a particularly interesting factor because it has Joule effects. And is heavily assessed in the VCE chemistry exam. So I encourage you to know this factor very well in order to prepare yourself for the exam. And in here, the definition of temperature is important. What is temperature? Temperature is the average velocity of particles. And the important theory is different particles travel at different speed or velocity. So imagine you have a pot of water at 90 degrees. You would still see some water vapor coming out. We know that water will vaporize at 100 degrees Celsius. So this means that in this system, which has an average temperature of 90 degrees, some water particles are actually traveling at 100 or even more than 100 degrees. And some are traveling at less than 90 degrees. So this is the idea behind this. And this links a very important theory, in chemistry, which is called Maxwell-Boltzmann distribution or curve. So the horizontal axis is kinetic energy, vertical axis number of particles with this particular kinetic energy. It looks like this. So this one has low temperature. This one has high temperature. So as you can see, even for a system with very low temperature, there are still some particles with very high kinetic energy, or traveling at a very fast speed. And this is particularly important. I want to draw your attention to. No matter how high your temperature is, there will still be particles with zero kinetic energy. Because kinetic energy is concerned with velocity. Velocity has a direction. So if your particle hits a wall and then changes the direction, then at a particular point in time, it will have zero velocity during this process of changing direction. So that's why when you increase the temperature, you are not shifting the curve. You simply flatten out the distribution. So this is very important. So always and the second factor is that the area on the curve is the number of particles present. So when you heat up a system, you would not change the area on the curve. This is also a very important observation. That's why when we increase the temperature, we flatten the curve to ensure that the temperature, the area under the curve is the same. So that's the two important things you need to know about the Maxwell-Boltzmann distribution. And then let's go back to the temperature question. So increase in temperature means you have the average velocity increases, which means you have a more frequent collision. But at the same time, you have a higher average kinetic energy. So more collisions have enough energy to overcome the activation energy. And the implication of this is that you have a higher chance of successful collision. Not only you have a more frequent collision, you also have a higher chance of successful collision. So those two factors come together to increase rate of reaction. And that's why that increase in temperature is particularly efficient, particularly good at increase the reaction rate, because it actually increases both the frequency and the successful rate of your collision. Now let's look at another factor, which is also very interesting. and also heavily assessed in the exam. Catalysts. So catalysts are interesting substances. They are not consumed during the reaction. But they can still increase the rate, help to increase rate of reaction. So how does this work? I recommend you to memorize or to try to understand this definition. Because usually in the exam, they can't ask you difficult question about catalyst. So as long as you can write this definition down, you should be fine. You can get full mark. So a catalyst distort the bonds of reactants. And provide alternative pathway with lower activation energy. Hence, a greater proportion of collisions have enough energy to overcome the activation energy, which increases the rate. You can also see how many collisions that actually have or exceeds the activation energy barrier from the Maxwell-Boltzmann distribution. So imagine we have an activation energy here. Then for a low temperature system, only a very small percentage of collisions have enough energy to overcome this barrier, hence a very slow reaction rate. But for a high temperature, we have a lot of collisions with enough energy to overcome the activation energy barrier. As a result, the reaction rate is higher. Keep in mind that the area under the curve represents the number of collisions or the amount of particles with enough energy to overcome the activation energy. So the area of the curve is significant for this Maxwell-Boltzmann distribution. So catalyst is the only factor that can actually decrease the activation energy. So it's kind of like cheating. Whereas for the other factors, you are either increase the frequency of collisions or increase the temperature. For catalyst, you are trying to find an easier way to proceed your chemical reaction, which is really, really interesting. You can also perhaps look at the energy change during an exothermic reaction, so such as the combustion of fuel. We already covered in the first or second video of this series. So this is without catalyst. So this is the reactant, this is the product. The products have less energy than the reactant, and so energy is released during this chemical reaction, which means it is exothermic. With a catalyst, you can see that the energy of reactant and product, they are the same, they are unchanged. So catalyst is not changing the reaction itself. Rather, it decreases the activation energy. So this is the activation energy. of this chemical reaction. And in this way, we can have a higher percentage of successful collisions. And that's when catalyst becomes very, very important and useful in real life applications. Without catalyst, many of the chemical reactions would be economically unviable to produce. So that's the 4 factors that can change the rate of reaction. We also need to know how to measure the rate. So let's use one example. Magnesium solid reacts with hydrogen chlorine aqueous solution to produce magnesium chloride, which is aqueous solution, and hydrogen gas. It's actually very easy to measure the rate of reaction for this particular chemical reaction because hydrogen gas would escape from the system. So we can look at the mass loss of this particular system to understand or to measure the rate of reaction. And then we can collect all the data and then see how the system changes. So this is a slow reaction. This is a fast reaction. There is a very interesting